We present a design framework for 3D printing of multi-material rod structures with desired active behavior. In this example, we observe how a box unfolds when put inside a warm water bath. When subjected to heating, an active structure can change its shape using the shape memory effect. This is commonly referred to as 4D printing. This box was created by warming up a flat structure and folding it into its target shape. At the end of this so-called training phase, the box is cooled down to fix its shape. When heated up again, the box actively unfolds back into its original shape. To enable the deformation into a box during the training phase, a specific material distribution is required. On the left, we have a box with a uniform material distribution. It cannot be folded into the desired target shape when simple forces are applied. However, the optimized box is softer along the folding joints, allowing it to be folded into the desired shape. We now present our pipeline for the design of active 3D printed rod structures with multi-material distribution. Here we use the Stanford armadillo to showcase our approach. First, we convert the triangle surface mesh into a Kosarat rod structure. In this example, we apply mesh simplification and project the dual lines back onto the original mesh. The dual lines are solidified into Kosarat rods. Now the user defines a target deformation and the corresponding forces that are applied during the training phase. Here we want the armadillo to bend its arms inward while maintaining an upright position when attached to the ground. With a uniform material distribution, the armadillo bends forward too much when the forces are applied. To achieve the desired deformation, we optimize the Yeung's modulus distribution by minimizing the deviation of the current deformation from the target shape. As the optimization progresses, the deformed shape converges into a target shape. With our optimized material distribution, the armadillo is now able to stay upright. To prepare the multi-material 3D printing, the armadillo rod structure is voxelized. Then, the Yeung modulus of each voxel is mapped to a ratio of the two printing materials. Lastly, the material ratio is randomly dithered between the two printing materials. We compare the training deformations of the uniform optimized versions of the printed armadillo. Here are the armadillos when actively recovering their initial shape in warm water. Next, we demonstrate how our framework can optimize a single model to accommodate different target deformations. Here we have a T-Rex model that is required to keep its head in the same position when its tail is lifted. However, when its head is lifted, the tail should stay in the same position. After optimization, the model is able to achieve these deformations. We compare the training deformation of the uniform and optimized versions of the printed T-Rex. Here is the optimized dinosaur actively recovering its initial shape in warm water. Active rod structures have a wide variety of uses ranging from product design to medical applications. On the left, we have a rod mesh that is designed to serve as the cast for the lower arm. We then specify a flattened configuration of the cast as the target shape. The material distribution is optimized such that the cast can be easily deformed into the target shape by hand. After being printed, the cast is soaked in warm water and manually flattened into its original target shape, which can be stacked upon each other or stored compactly for transport. This flattened cast can be restored to its original shape anytime by reheating it. When required, the medical cast can be warmed up by a warm towel or heat pack, which allows it to actively deform back and wrap around the patient's arm. Our framework can also be applied to non-organic engineering models. Here we want to create a spring structure that buckles in the middle when pushed down. This nonlinear deformation into an unstable equilibrium state is difficult to simulate and achieve. Using a uniform material, the spring buckles at the top and bottom half when subjected to a force. However, with the optimized material distribution, the spring is able to buckle correctly in the middle. Thank you for watching our presentation.